these are our internal reactions for the elements, right? So we can take those out, and we end up, leave it up there, right? So we end up here. So those all go to 0, collapse down to 3 equations and 3 unknowns. And then the book talks about, I don't know, what did it say? Multiplying by the inverse and doing this, that, and the other thing. The computers are set up to solve the problems in a certain way, and so they can manipulate it however. I mean, we could simply start a Gaussian elimination and, you know, solve for what these are going to be. I don't remember how long it took me to write this out, but it took a long time. You don't want to have to do this by hand very often, or as little as possible. So, but okay, so questions. I mean, does that make sense? How it got expanded, how we put it together, why we did what we did, and how we got to where we are? At least a little bit.
I just don't think I could have done it with what the book gave us.
The book skips a lot of steps. The other thing that really helps is, at least for me, is if you put, you don't have to necessarily have F in, but if you start putting in your deflection vector, then you know, you can start doing the, you know, making sure that you have things in the right position associated with the correct displacement location. And so that helps me a lot. So yes, I totally agree. The book skips a lot of steps. There's a lot of things that you have to have known from taking linear algebra and some other math classes to be able to make it through all those steps. And that's part of the reason why I wanted to, you know, show that, demonstrate it, so that you guys can at least see how that's happening and how we get there. So it makes a little more sense, even if, you know, we're not really going to do it, but it helps put the pieces together and understand, you know, what's happening and why you're going to set up, you know, your nodes and elements in a certain fashion, if you will, so that things will go through. Okay, so
is it always going to be left to right, or
no? You can go right to left. You can start top to bottom. Just be orderly and organized about it, and don't, you know, jump all over the place, and then you'll be okay. And you know, you don't have to, you know, this is, you know, 1, 2, 3. Oh, gee, well, should I make this one 4 or this one 4? Or, you know, 5 or, you know, well, I want this one to be 6 and that one to be 7. It's don't get too wound up about it, but just be orderly and organized about it, and it'll be fine. I think I know that helps, and this book is, I don't remember how old it is, but I'm sure the software has progressed fairly significantly since then and can probably do some of that for you. I don't know. Like I said, I don't know enough about the software side to really speak to that. But
have that top drawn, I would have fixed both ends just from how it's drawn. Wheels
well,
on the right, like that.
Fixed both ends?
Well, to me, that upper drawing, it's a fixed truss between 2 locked points.
Well, for our idealized applications, you know, when we're doing mechanics of materials and statics and some of those, yeah, we can certainly fix this, but then it becomes an indeterminate problem and a lot harder to solve. Whereas if we leave this as a roller so that it can move in this direction, then and only, you know, clamp one end completely, then we can solve these with analog calculations much more quickly and easily than if we make. Now the computer doesn't care, and yes, you could constrain it, you know, completely at this end, and it'd be fine. But So I think some of that's just sort of a, I don't want to say leftover from analog days. But the other thing is too, is I mean, anytime you go across a bridge, you go across the expansion joints.
Right.
So they're in there as part of the calculation anyway. So it's, yeah. Okay. So this calculation, all right, so I didn't get to write this all out, but we're gonna try to work through it here and see how it goes. Hopefully, we don't get ourselves in too much trouble. It seems to work pretty well without this light even on there, so we'll go that route. So, let's see, we're gonna do the first problem by hand, and then we're gonna do it in Patran. Okay. Okay, so this is our picture. If you wanna sketch that or open your book or whatever you want to do, this is what we're going to work through. And we'll at least, well, we should be able to work all the way through it. And then we'll do it in Patran and confirm our results. So, let's see. So we've got 3 elements. So how big is our matrix going to be when we're all done? So we have, what, 3 elements? And each element has a node at each end. So we've got four nodes, and each one of these can move in 2 directions. So 2 times 4 is going to be 8. So we'll end up with an 8 by 8 matrix in the end. Okay. All right. Let's go back to the green sheets. Okay. So remember, we started out, and the chapter starts out talking about K equals AE over L, right, for our stiffness. And they define so they give us a cross-sectional area. Oh, it even says it'll be an 8 by 8 matrix. Gives us the material. Let's see, 2 of them are aluminum, 1 of them is steel. Okay. So if we want to determine, so let's figure out what K1 is, right? So element 1, and they said it's aluminum, and our cross section is 1, it looks like, right? So 1.0 inches squared. My E for this is aluminum, so 10 times 10 to the 6 squared. And our length, 20, right? So that'll equal So what's my area for the second element? Oh, whoops. I think I did it backwards. This should be 1.5. This is 1. What's my material? One and 2 are aluminum. Okay, so this is 10 to 10 to 6. And how long are we? 40 inches, right? So 2.5. Now this one is steel. What's my length? That's the bags. So it's a 3, 4, 5, 6. Okay, so that makes sense to everybody what we're doing? Because we're going to treat these.
So are your units for K, PSI?
Pounds per inch.
Okay.
Oh, not square, sorry. Pounds per inch, because it's a spring constant. Thank you. Thinking E. So we're treating our truss like a spring element, and this is going to be our stiffness of our spring, our K, for our truss element. So now we have to set up or begin our matrix, right? And if we start K1, so what do you think K1 is going to look like? What's my 4x4 matrix going to look like?
You zoom in a little.
Sure.
Perfect.
That help?
Yeah.
Okay. So if I'm going to put a 4x4 matrix up, what do you think it's going to look like? Do we have an example or a sample in the book? What should I refer to?
4x4?
What, yeah, but which, so they've got, example 3, or well,
3.3.
3.2, 3.4, 3.5, 3.14, 3.15. We've got all these different examples. Where are we going to start? How do we start this? Do you think?
3.3.
3.3? Right. Well, yes, 3.3, but we're going to we'll back up to 3.2 because that one's developed. It's not the short terms, right? Because we want to put out the K's and the zeros and do all that, right? So which is it going to look exactly like what we have there in 3.2? Because which nodes am I going to for? So this is K1, which one did I mark as 1? So we're going to be, this is going to be U1, V1, and U2, and V2, right?